So this talk will be about model training in Snowflake with a focus on scale. My name is Jeffrey. I'm an engineering lead on Snowflake ML. Been with Snowflake for about 2 years, working on different parts of the Snowflake ML stack. And I'm joined by Benjamin from Les Schwab.
Hi, I'm Benjamin Murders. I'm a data scientist for Les Schwab company, and I've been working there for a couple of years. I'm pretty excited to talk about how you can scale and train your machine learning models very efficiently.
Cool. In terms of agenda, today we'll recap the various features we have for model training within Snowflake ML. We will do a deep dive on one of our new features that we've been collaborating with Benjamin quite a bit on called mini model training. And then I'll hand it over to Benjamin to talk about Les Schwab's experience with container runtimes, Snowflake Notebooks, and these new model training features. And then we'll wrap it up with a demo that Benjamin will be doing for us. So cool. Quick recap of the Snowflake ML stack. So all of the training capabilities that we're going to talk about are part of the Snowflake ML stack. Snowflake ML is a very comprehensive end-to-end platform for doing ML all within Snowflake. If you look at the middle layer, you can see all of the APIs that allow you to do the entire journey from feature engineering to model training to deployment and beyond. And you can use all of these capabilities from different developer surface areas like Snowflake Notebooks or external IDEs. Today, we'll be focusing mostly on the training APIs, container runtime in particular. So, as I said, the container runtime is really very central to how we do training we recommend customers do training in Snowflake. So, what is the container runtime? The container runtime is a pre-built environment that is purpose built for machine learning. At the most basic level, you get an image with a bunch of popular ML packages installed. And what we every time you start a container runtime, either through a notebook or through a job, what happens is we spin up an ephemeral Ray cluster behind the scenes, and then we use Ray for managing our distributed compute infrastructure. And on top of it, we have layered APIs for managing data ingestion very effectively and distributed training that we will go into a little more detail on. So this is using best of breed open source tools. And then what our focus has been on making sure that interacting with Snowflake data and scaling out on Snowflake infrastructure is very seamless and easy to use. So diving into data ingestion a bit. So why is this very important? Whether you're doing your feature engineering, whether you're doing large scale data processing, whether you're just doing open source model training, very efficient data ingestion is critical because otherwise you'll see a lot of performance bottlenecks. So what we have done is we have implemented what's called a data connector API. The data connector API works off of all Snowflake sources, be it a table or a Snowflake stage, to ingest training data very efficiently into training processes. In this example, you can see this is just working off of a Snowpark data frame and materializing it super fast. In terms of performance of these things, so this is a published benchmark we have done a few months back. So on the x-axis, you can see the size of the data set. Y-axis, you can see the data ingestion throughput. You can see at very small scales, sub 1 GB, these things don't matter. It doesn't matter how you materialize, whether you use the API or not. But as you get to 10 GB and 100 GB scales, these matter a lot. There are orders of magnitude performance improvements that we have seen with our data connector. So this is really the kind of a theme you will see throughout the talk, that our focus has been to make sure that you can start with best of breed open source tools, and then you don't fall off a cliff when you hit that scale. Now, these APIs, as I said, are easy to use both through a notebook as well as through an ML job that can be kicked off from any IDE. Coming to distributed training, so you can use the data connector, you can use your open source libraries to train the model. At the point you want to scale that training out to multiple nodes, that is where our distributed training APIs would come in. So what we have done again is we've implemented a bunch of wrapper APIs that look very similar to the open source variants for popular frameworks like XGBoost, like GBM, PyTorch, etc. And what these do is they take full advantage of the data connectors we spoke about before, but they also do resource utilization on the infrastructure you're running on very effectively. In this code snippet, you can see this is for standard XGBoost training. It is a standard estimator style interface. And the only additional parameter you have to provide is a scaling configuration that if you want to do any differentiator scaling other than the default scaling we provide, you can configure that. Quick example for this kind of a benefit. So this is comparing running open source XGBoost versus Snowflake ML's distributed XGBoost on varying sizes of the data. So on the x-axis, you can see increasing size of data sets. On the y-axis, you can see the training time. And the blue line at the bottom is using the Snowflake ML API. The other line is using open source. And this is running XGBoost training on a GPU. And you can see the scaling characteristics are much better for the Snowflake ML API. And that's not very surprising. All that we are doing is we are taking advantage of this was run on a GPU machine with 4 GPUs. And so without you configuring anything, we will shard the data appropriately. We will place the compute on all the devices properly. And that's the benefit you see. So it's really effective use of resources. That's where the magic comes, right? Similarly, for hyperparameter tuning is another common use case where you're training across different parameter combinations, which is quite popular in certain cases. These hyperparameter APIs now, they use the optimized data connectors, they use our distributed trainers, and then they're also able to scale out on our infrastructure. Um, you're not limited by choice of optimization strategies. You can use your standard grid search, random search, or even Bayesian optimization strategies that you can find in popular hyper optimization packages. So now that we've covered data connectors, distributed training, hyperparameter tuning, let's talk about many model parallel training, which is a new feature that we now have in preview. So what is many model parallel training? One of the very common use cases we've heard from customers is your data has an inherent partitioning to it. So this could be your data is partitioned by, let's say, customer, geography, or like stores, like in Benjamin's case. And you want to train one model per partition. And these could be for hyper personalized recommendations, or it could be because these different partitions really have different characteristics that a single model is not able to capture all of the nuances. So you'd want to train one model per partition. And when you do this naively without this sort of an API, you would have to take care of all of the orchestration when you're doing it, at scale, hundreds to thousands of models. You have to, do the fault tolerance. You have to do the bookkeeping. You have to do the retries. So we've had a lot of pain points from customers on this. And also in addition to that, inefficient resource utilization. So what we have done is we have implemented a parallel training API. Again, same concept. We want to abstract the complexity and make it really simple for you to run this sort of a workload. So what we have done is we have basically implemented parallel training orchestration on top of Ray. So we use Ray's primitives for scaling out this compute and pipelining this whole process very efficiently. This is something that you can also do, but it's very hard to sometimes get right and run in a stable manner. But this complexity is abstracted away for you, and we can look at the API very quickly. So in terms of API, you point at a table, you start with your standard Snowpark data frame. You could write your training code. It's a user training function. You could write any code you want. It can use the data connectors. It can use the distributed trainers that we talked about. Doesn't matter. The example shows a simple example where you're materializing to pandas. And then that's it. You can run the mini model trainer by passing in that user function and then specifying your partition key. In this case, there is a location ID. It could really be any other partition key as well. And that's it. Behind the scenes, Snowflake will take care of all of the pipelining, prefetching, and so on. And when you run this API on a Snowflake notebook, we also give you observability out of the box. So it's very easy for you to see what is happening behind the scenes. What is the progress on data ingesting of different partitions? What is the progress on training? You can see the resource usage. This comes out of the box on a Snowflake notebook without you writing one line of code, right? So this is kind of the theme that you see across, right? We are trying to see where is it that we can simplify continuously without taking away flexibility. These are some results we have seen on synthetic data. So in this example, this is comparing a very simple, just a for loop over all the partitions with our mini model training API. The blue bars show the ones for the serial training, and the orange shows ones for the mini model trainer. You can see on the x-axis we are scaling the partition size. So when you're at small scales, 200,000 rows, a million rows, it doesn't matter a lot because sometimes the overhead of orchestration takes over the benefits. But as you get to more serious scales, 5 million, 10 million, you can see the training time almost gets cut in half, right? Similarly, when you scale the number of partitions, so when you want to go from 2 models to, let's say, 1,000 models, similarly, you can see the benefits of this sort of an API because we are not doing a dump loop across all the partitions. We are prefetching and pipelining this very efficiently. And what's even more cooler about it is you can just throw more machines at the problem. So in this, the green bar shows running on 2 nodes, the orange shows running on 1 node, and you can see almost a linear scaler because this is a highly parallelizable workload. So we are very excited about this API. Don't believe all the numbers you see here. Go try it out and see for yourself. With that, I'll hand it over to Benjamin.
Hi, I'm Benjamin, and I'm here to talk about how you can save on costs and train efficiently at scale for multiple machine learning models. I'll start with a little bit of high information about the company I work for, just to give some context and why this is relevant for us. We're a retail tire company. We have over 500 stores across 15 states, and our founder, Les Schwab, created the company over 70 years ago. So what makes Snowflake so special? Why would we want to use Snowflake to do this ML infrastructure? Well, our data is in the Snowflake at the moment. So anything we do in Snowflake without having to pull that data back out to do inference or model training is going to save us on time and costs. So that's one of the main points is why we would want to use Snowflake's ML infrastructure. We can, using their APIs and frameworks that they have in place, we can significantly decrease training time as well as train more efficiently without having to consider all the complexity of a multi-GPU configurations. This is really important for us as we like to use very advanced models for our forecasting. For example, forecasting across 500 plus stores, we're playing around with sequence-to-sequence PyTorch neural network models. Really need to take advantage of something that has more compute power and using a multi-node, multi-GPU environment without having to play around with debugging or troubleshooting or any of the other issues that you might run across. Being able to just use something out of the box that just works has saved us a considerable amount of time. And not to mention the model registry, being able to store models in a production environment with version control. So features of being able to use a container runtime in a Snowflake notebook. So this is where we've been doing a lot of our work. There is ML jobs to be able to do this remotely, but using a Snowflake notebook is considerably easier to try to use the multi-GPU environment. When you use a container runtime for a Snowflake notebook, unlike using a warehouse where you can have the Snowflake Anaconda repository or Snowflake Anaconda channel, you can install virtually any kind of pip Python package. This makes it very versatile to be able to use custom forecasting methods such as darts. I'm a big fan of writing SQL, so I love the SQL to Snowpark data frame functionality. So whether that's 10 lines of SQL code or hundreds and hundreds of lines of code or just a view I created outside the Snowflake notebook, um, I, I'm able to call on that code, get the result set, and turn it into a Snowpark data frame. And what that means is that the data is not being pulled into the Snowflake notebook. So whatever compute pool I have at the moment for the Snowflake notebook environment, I'm not having to waste memory and use up billions and billions of data in that notebook. It's actually sitting on the servers within Snowflake and it's not being pulled in at that moment. There's of course Git integration and then the GPU parallelization, which I'll get into more details in some further slides. But I really want to emphasize how easy it is to create and use a multi-GPU environment for training models and as well as doing model inference using compute pools and Snowflake notebooks. This is a screenshot just to show you the configuration when you are configuring a Snowflake notebook to use a container runtime. So instead of using the default option that they had previously, where you can select a warehouse with whatever warehouse size that you're wanting, you select you want to run on the container, and then you select your, right now there's only 2 options for the runtimes, a CPU bound and a GPU bound runtime. If you select GPU runtime, that will typically have a lot of the CUDA support. So if you're using PyTorch or TensorFlow, it'll have those libraries and SDKs in there as well to be able to run on GPU. But then you select your compute pool configuration, which you can configure outside. There should be some default ones that you might have already in Snowflake in existence now, but you can very easily, with just a handful of lines of code, create your own custom compute pool configuration if you're needing more power. This is the process that we typically have been adopted for training models in Snowflake at a high level. If there is not a compute pool that already meets our needs, we can create a custom compute pool, but otherwise we'll select a default created one that we have in existence, create the Snowflake notebook, and then we'll pull in our training data that's already in Snowflake. So we don't have to pay for any other costs or anything like that. We're already using the data that we have. And then whether we're training one model or hundreds and hundreds of models, that's when we do our model training across a multi-GPU environment. And then we store that model into the model registry. If it is a situation where we are training more than one model, such as model partitioning, so in the case of Les Schwab with over 500 stores, we'll partition at the store level. We can store that into a custom partition model class in the model registry. So instead of storing 500 plus models in the model registry, they're all consolidated into a single custom model that we can derive inference from. And the inference can be derived either through SQL or Python. I'll get into more details on how you can do it through SQL, as well as demonstrate that in the live demo. But I'm a huge fan of being able to do that in SQL. I'll get into more details about that, but it's very exciting to be able to use SQL to get model inference without having to use some kind of Python SDK. So use cases for our approach to using the custom container multi-model partitioning is that we can actually, for time series forecasting, instead of getting an array value as the output, so let's say we're forecasting for the next 10 days or the next 30 days, we can actually return that as a table object result. So that way we get 10 rows for the every day of the next forecast instead of an array that I would have to then transform into a row format. And this scales across multiple partitions. So if I have 10 stores I'm forecasting for the next 10 rows, that would be 100 rows that I would get for each partition, 10 rows for each of those 10 stores. And then, of course, the being able to derive model inference to SQL, it looks just like a user-defined function, any kind of UDF. You're able to invoke it through just typical SQL as you're pulling in your data. And the reason why this is so huge for Les Schwab is that we can embed our model inference, like forecasting, with other important metrics and KPIs. So that way, executives, whether it's their CFO that's looking at revenue forecasting and trying to understand what's and trying to make the business decisions on what's actually going to be happening in the future, we can display that data onto that on that dashboard. And whatever dashboard you're using, whether it's Power BI, Tableau, Hex, um, you can do any BI tool that accesses SQL, you can access your model inference. For the custom model partitioning class object, there are two different types. There's a stateless and stateful. Les Schwab has adopted the stateful partition modeling approach, which is where you train the model and then you're storing that trained model for inference. This will, and of course, as I already mentioned before, you can consolidate any number of arbitrary partitions into a single consolidated model object for the model registry. Now, when you are doing multiple partitions, so let's say I'm doing over forecasting for over 500 stores for sales. When I do model inference, I'm not loading all 500 plus models at once. This saves on cost and time. I'm only going to load the corresponding and applicable store for getting that sales and forecast. So that saves you on cost and time. This is an example code of being able to use the PyTorch distributor. I've had really great luck in being able to use this to scale a multi-GPU configuration environment. So within the Snowflake notebook, I configure I select the compute pool and the container runtime for GPU. And then I configure the hyperparameters for the number of nodes, number of workers, and number of GPUs, assuming those are available for the given selected compute pool. But I'm able to then run off of I pass in the training function, and then I run and I pass in in this example use case, I'm sharding my data, and those are actually two Snowpark data frames, a train and validation data sets. Those get loaded in, and they get turned into Panda data frames and transformed further into a format that the model can accept. And you're able to pass in hyperparameters. These have to be string values, so you do have to be cognizant about when you're passing in float values, such as like batch size or learning rate, and then converting those back to a float within your train function. But you can pass in hyperparameters, and this works out of the box without any customization at all. You just define the compute pool, run it in the Snowflake notebook, and it just works. This is what is being discussed, a preview API for mini model training. This is invaluable for Les Schwab when we're trying to scale multiple models. So forecasting for 500 plus models for sales, as an example, all we have to do is pass in a train function. We reference a stage to store the models when they do get trained, and it will run across all available nodes that are available for a given compute pool. So whether we have 100 of those and we have our 500 stores, it'll run across all 100 available nodes and then run them in parallel. So I'm not having to iteratively train on each store. I'm able to run and train on multiple stores in parallel. The benefit of being able to reference a stage here is that when the model, if this process succeeds and you've successfully trained your 500 plus stores, um, it'll store it into the stage. And if something happens in your kernel, your Snowflake notebook bugs out, you lose internet connectivity, or a subsequent cell fails, you don't have to rerun this process. Those models are already stored, and you can go into your stage, grab those files yourself, and you can load them up into the model registry directly if you wanted to. So that's saved amount of time, and it helps considerably when you have to do additional troubleshooting after the fact, and you don't lose all of your progress because it's not being stored in local memory. Here's the example SQL code for a custom partition model, be able to access that through SQL. It's very straightforward. I create a CTE wrapper for my input data, and then I have a common table expression for the forecast I'm wrapping around my actual code. I reference the specific model, and then for the version, you have a couple of keywords that you use, default or last, or you can explicitly define a specific version that you want to call on. And then you do your select for the output result of the CT for that I'm passing for the input data. But this is the important part for a custom partition model. You need to add that comma, and then you have your table expression, and then within that table expression, that's where you do the model inference, where you invoke it just like a normal function. I'm passing in my store ID because that's the partition I'm using for this example, and then along with any other features that I need to pass in. And then I'm using the over partition by store ID. So it's like a window function because it is partitioned. It's not just a single model that I'm accessing. And then the result return, let's say the forecast is for 10 days and I'm doing 10 models, we would expect 100 rows out of this when I do my select star from the forecast data CTE. And then I'll show this as well in the live demo. All right. So here is an actual live notebook. I already ran it, so everything's cached and ready to go, but it is in fact live, so I could lose internet connectivity. We'll see what happens. So what I'm doing here is I'm doing two partitions for two synthetic stores with synthetic data. I'm deriving that synthetic data using a couple of UDFs, and I'm deriving all that within SQL. So I set my random seeds. I wanted to show that I am in fact using a GPU environment in the Snowflake notebook. It's only one GPU, it's a small compute pool configuration. And then I get my active session. This is invaluable to be able to use when you get your active session because you're not having to pass in your own credentials. Whether you're working in an environment, you don't have to deal with secret management or anything like that. It'll just pull in the credentials for the active user that's in there. Something I did want to show as a new preview feature is the ability, it's kind of like a task manager where you can see your actual GPU, memory, CPU, all the usage that's happening in the notebook in real time with different intervals that you can look into the past. All right, so here are my two UDFs that I'm going to be using that I call on to create my synthetic data for my two stores. And there are two distinct sinusoidal functions. And then this is the result set when I call on the SQL off of those, when I create an array of, I believe it's 1,000 rows for each store. And then I have two columns. I have my sales column, and then I have my noisy column that I'm adding noise to the sales column, just so that I can generalize a little bit better with the model training. And then I'm transforming the result into a snowpark data frame. And then to visualize the data to see what they kind of look like, it'll take a moment to load here. Then we have to rerun it. So this is what the first store looks like. Obviously, that's not typical of any kind of store, but it's a repeating pattern. So our model is going to be a really vanilla sequence to sequence model neural network using PyTorch. It'll just be a basic encoder taking in a sequence of past historical data and then there'll be a decoder that'll return an arbitrary sequence of output. So if I wanted to forecast for 30 days or 100 days, whatever I pass in, it'll return that value. This is what it's going to look like for the store number one, the second store, so that you can visually see that it is a little bit different. It's not just a phase shift. It is two distinct functions. And this is what the store one with the noisy data looks like, just so you can see what the noise actually looks like for the sales data. So here I'm configuring the MLP that I'll attach to the end of the decoder, so that every time the decoder runs, does its inference, it'll pass it through an MLP block because this is a regression problem. And I will share a barcode for referencing, where we're going to attach a link if you use that barcode, so you can access this this notebook code. So it's not, you don't have to try to capture everything right now. You'll be able to reference it later. Here's the encoder. Like I said, this is a basic encoder. It's not really taking any covariates or any other kind of features. It's just a straight one-dimensional LSTM encoder. And then the decoder, like I said, it's just when it takes its inference, it passes it through an MLP block, and it's also an LSTM as well. And then my LST time series model, where I combined my encoder and decoder together, and then my iterative loop to get for the next 10, 30, 45, 100 days, however far out I want to go. And then my time series data set, where I pass in and transform the data from the Snowpark data frame into an array in a format that the model can consume. Here are just some basic hyperparameters. It's not a robust model. It's only got 32 hidden units for the hidden layer. It's only got one layer, and the learning rate is pretty high. This is probably where you would actually really want to focus on. This is going to be my train function. This function is what I'm going to be passing into the mini model trainer API. So I define my model in there. I define my criteria, so my optimizer, and then as well as a learning rate optimizer. And then I take my data connector and I return the pandas data frame, and then I take that and create a NumPy array where I pass that into my time series data set into a format that the model can consume. And I also create a data loader just so that I can iterate and batch accordingly with the model. And then I do my iterative training loops off of the models to train on. And I'm doing print statements. And you can access these when you use the mini model trainer API. Anything that you do print statements on will actually be captured in the logs. So you can actually capture that. And I'll show that in a moment. Here's where I create my stage. And then this is the function for calling the model for the mini model trainer API. I have my train function being passed in there. I'm referencing the new stage I just created and then the stage name. And then I pass in my Snowpark data frame, and I reference that the column to look for to partition by is the store ID. Here's the graphical user interface that will show up, that when you call on the API, this will update in real time. It'll ingest the number of data sources that you're using, the number of partitions, as well as the number of training partitions that you have. And here I access the logs from my trainer model object for the main model training API. And then I can access the keys, which in this case is the store IDs. These are string values, so my store IDs are just 0, 1 for store 1 and 2. But you can use any kind of string value you want for your partitioning. And then I just grab those models off of the trainer object and I store them into the local dictionary. So that way I can store them into the model registry as a custom partition model. I do some visualization off of a validation and test data set just to kind of see how it works. The hyperparameters are not optimized for this, so we'll just see what that looks like. I'll just have to reload it here. So it seems to extrapolate pretty well, but it also is a repeating pattern, so there's nothing overly complex about the underlying data structure, but it did actually fit fairly well. And then we're going to store this data into the model registry. So I create a new time series data set that's specific for the model registry. And then my custom partition model, where I access the model ID so I can load the specific model for the specific store without having to load all the models at once. And then I get inference. And then I return a pandas data frame. This is a custom explicit model signature for the model registry. You don't have to do this. You can pass in sample data. But I like to be explicit when I'm doing very custom things. But that's just an example of what that looks like when you explicitly define what you want your signature to look like, what kind of input data it is, what the values are, what the shape is, and then what the outputs are. Now, I already did store this model into the model registry, so I'm not going to exit this code, but I wanted to leave it there just so as a reference for anyone who wanted to kind of see what that looks like. You create your registration object for the model registry, and then you log the model, and then you load in all the other arguments necessary to do that. This is the part where since the model is in the model registry, it does actually exist in there, and I'm accessing it through SQL directly. This is just a snippet within this markdown cell. I can open up the SQL cell actually if we wanted to go into the details, but that is the actual model name, the database, the schema, the model name. I'm referencing the last version. I'm selecting the store ID and the prediction and forecast index. So I know that the ordering of the output for the multi-day forecast is, as well as doing my table function, where I'm predicting off of each partition. This is the result from the SQL cell, but if I wanted to look at the actual SQL, just so you know what that looks like. Here I'm generating the data, I'm doing an array, so I got all my X and Y values, and I do my transformation with my two UDFs I created for each of the respective stores, and then I unpivot those data out, and then I access and create the actual sales data with inference data is what I'm essentially doing here. So I do the forecast, and then I combine the actuals with the forecast, and then we can actually visualize to see how well the model actually referenced that data. Might have to run this. Okay, and it's running. Might take it a moment. Okay, it worked. And I'm loading the result set into a Snowflake data frame. And then we can visualize for the first store partition how well the inference actually fit with actual sales data. And it actually fit pretty well. All this that you're seeing off of this chart is straight from that SQL code cell block, not from any of the modeling I did before. It's calling on the model in SQL in the model registry and doing the inference, and then I'm overlapping that with the actual observations of the actual sales data. And then this is a store too. And we could have done a little bit better job, but it at least kind of modeled it a little bit. All right. What the roadmap looks like for Les Schwab with respect to using the multi-GPU environment, the mini model trainer, is that we're going to be able to simplify our processes. Right now, that's a little tedious and complicated, and we can simplify that significantly by using all the infrastructure in place within Snowflake. We're going to be able to minimize our training time significantly by a multi-factor amount because we're able to train off of all of our stores in parallel at once. And then we can have a production environment that we've already been using to be able to store our models with model versioning. This is the QR code I mentioned earlier where you can reference and access the, we're going to have a link. It'll take you to a quick link section with other relevant, useful information, but we'll have a link in there to the GitHub repo with this code. So that way you can access it and see what that actually looks like. Thank you.